Hi there, I hope you're having a great day. In this video, we'll be taking a look at UProbes. Along with that, we'll be learning how we can send data between our kernel and user space programs. And we'll be looking into getting around some of the quirks of the BPF verifier, things like unrolling loops and all. So in order to make this somewhat of a project-based learning experience, we're going to be creating an application that intercepts all SSL write calls of the OpenSSL library. So just an example of what that really means. I've got my eBPF application running, and what I'm essentially doing is I am intercepting any calls that are made to actually encode a certain amount of bytes with SSL whenever an application is using the OpenSSL library. So an example would be when I perform a curl on https google.com, I can intercept in my eBPF program the data that has gone to the SSL write function, and I can get that in plain text. Now, obviously, otherwise you would not be able to sniff this data and actually get the SSL encrypted, sort of the SSL payload in plain text. So we'll take a look at how we can get all of that out of the application. So right here in the SSL documentation, this is the exact method that we will be intercepting, that we'll be placing our uprobe on. It's called the SSL write method, and this is called whenever an application essentially calls the OpenSSL library to encrypt the text in a certain buffer. So let's take a look at the OpenSSL source code for the same method. It takes a data structure called the SSL structure, and this essentially holds your SSL context. So it will hold the keys and all of those things. We don't really need that right now. What we do care about is the fact that it has a void buffer that contains the data that needs to be encrypted, and it has the num, which holds the number of bytes that are to be encrypted. So with that knowledge, let's go ahead and create our eBPF project, and we'll get started. This is this is going to be a very implementation heavy video. I'll have checkpoints in the description below, so you can skip forward or backward depending on your convenience. Cool. So let's open up our terminal, and we're going to use the same command line snippet that we were using to create our application boilerplate code essentially. So I'm going to call this, the generate command, and I'm going to call this, let's wait for it to load first. I'm going to call this OpenSSL BPF. That sounds like a good name. Let's use a uprobe here, and this is going to be a attachment on the OpenSSL library, and we're going to place it on SSL underscore write. And beautiful. So now it has created the project for us. Let's open that up. So taking a look at the user space code of our BPF application, we've got our boilerplate code ready. It attaches to the SSL underscore write method of the OpenSSL target. However, this is not a valid target. We're going to have to take a look at where we need to, where the exact target is going to be. So for example, in my case, I'm always performing a curl to test my application, right? So I can just do this and take a look at the target name that curl actually uses. So in my case, I'll use LDD, and as you can see, let me just add a grep on SSL. So it uses a library called libSSL. So instead of OpenSSL, the target over here is supposed to be libSSL. Cool. Now that I've got that going, I can take a look at the eBPF code. This is very straightforward. All it's doing is printing out that the SSL write method has been called. So let's build this application real quick. From the README, I'm going to copy the script that's already generated, copy the command that's generated. I'll just paste that here. And now that the compilation is complete, it's going to ask me for my password as usual. Yes, let me add the rust underscore log equals info variable here, and that should do it. We should be getting our output. So we're getting an output whenever the whenever the SSL underscore write method is called. Now let's take a look at accessing the variables real quick. In the same vein as we did with kernel probes, we have access to the variables that have been called in the user probe as well. The way to access that is similar to the kernel probe. You get the probe context and you can extract variables from there. So we're going to do the same thing with our application here with the probe, with the user probe context. Right from our documentation, we can see that it is SSL underscore write. The first one is an SSL structure. We can ignore that for the most part. We need the buffer and the number of bytes that have been written, that want to be written. So let's do that real quick. We can extract the buffer. So that's going to be let buff. We're going to call it buff pointer. And that's going to be a const c void, which is going to be a context dot arg 0. And if that does not exist, if there's a runtime error when we're trying to extract that, we can just throw an error which is like 1u32, which should be fine. And let's import that. Cool. Let's add a question mark here. And yeah, this is going to be argument number 1. And we can copy this over and we can have a num bytes ptr, and that's going to be our argument number 2. So let's real quick do a null check on both of these. So if b buff pointer is null or the number of bytes is null, we can simply return an error, and uh, that should essentially convince the BPF verifier to not be mad at us. Cool. So now that we have all of this data, let's take a look at actually sending this data onto our user space application. So for now, let's just log this data and then we're going to work towards sending it eventually. Let's create another method which will take the context and it will take our variables, which is the buffer pointer and the number of bytes. And you know what, I'll just make this a method here. So a function, sorry, and it's going to take a probe context, num bytes, and the offset. Actually, let's get rid of the offset. I don't know why I thought of that. Let's do this for now. Cool. So at this point, we come to an impasse. There's a method we can use to actually sort of read the data out of this pointer that we have for the buffer, and it's called the BPF probe read kernel. Sorry, read user, similar to what we had in the previous video where we used a BPF probe read kernel. We're using a BPF probe read user to get data out of the user space, and it's a buffer, so you can essentially give it the pointer to the start of the buffer along with the number of bytes to actually extract that number of bytes out of the application, sorry, out of the user memory. So let's do that. We are going to import this in, and this is an unsafe method. Let's add our unsafe block real quick. And cool. So the data that you need to give it is the buffer pointer itself, which is the start of your, it's essentially the start of your buffer. And right after the buffer pointer, it has to be a constant U8, I believe. Let's take a look. Yes, it needs a constant U8, and it needs an array of U8s, which will essentially hold all of the data that we're reading. Now the problem here is this needs to be a statically sized array. It needs to be something that is provisioned on your stack and not on the heap, because you don't have access to much in the way of heap memory. So if we were to create some sort of, let's say, an internal buffer, so let's call it an eBPF buffer. So we're going to call it the eBPF buffer. And this is going to be a U8 with, let's say, the maximum size of payload that we might foreseeably be actually decrypting. So let's just make it 16384. That's 16 kilobytes. It's a huge buffer. You're probably not going to be encrypting 16 kilobyte payloads at once. So let's do that. Oh, sorry. Let's move this here. And that is going to be a U0, U8. sorry, 0 U8 U8 with 16384. And let's see. So the challenge here is, let's get rid of this. I don't need this type hint. Cool. Now that I have this going, I need to give the pointer of this particular buffer to the BPF probe read user buffer method or function. So let's do that real quick. I can just do a mutable. Sorry, I don't need to give it a pointer. I need to give it a destination. So I need to give it a mutable reference. So I'm going to give it a mutable reference to my eBPF underscore buff. And yes, that should be it, except I need to make this mutable. Cool. So now that we've got this, let's try printing, let's try compiling this application, and we'll see what sort of challenges we might face. Right. So right away, we've got a lot of problems. The first one is that this particular buffer is too huge to be on the stack. So if you remember, we had noticed that the maximum buffer size that you can have is 200. The maximum size that you can provision on your stack is 512 bytes. So a 16 kilobyte buffer is just not going to cut it. So let's make it a 200 byte buffer. So this essentially means that we'll end up losing a lot of data. But get to that. Let's solve that problem when we get to it. One more thing that we might want to do is, since this is a buffer and we need to refresh, there's this whole concept of refreshing the buffer over every loop. We're going to have to provide the number of bytes that it needs to process, which is going to be a dereference of our num bytes pointer. So in here, let's just send the dereferenced value, and instead of making this a void, we can use a usize. That would be great. And this can be dereferenced. This is an unsafe operation, so it's going to be that, and we can cast that as a U8, which it won't let me. Sorry, we can cast that as a usize. The problem here is going to be that it cannot move, so we're going to use a reference. And all right, we should have used an integer here as a cint. So then I can cast this as a usize. Cool. Let's see if I can do that. Great. So import cint. Beautiful. So now I've got my number of bytes here, and I can essentially pass this into here. Great. So now I'm populating this tiny little buffer with a certain number of bytes. So once I've got this going, let's try and actually send data onto our user side app. So let's create a structure that will be passing around between our user space and our eBPF application or our kernel space. I'm going to put this into my lib.rs, and that's going to be a pub struct of let's just call it SSL data. I think that's fine. So this thing is going to have a buffer of 200 bytes, the same way that we had, since our eBPF buffer is limited to 200 bytes. So I'm going to call this a buff, which will be a U8 of 200 bytes. And we'll make everything public for now. And finally, we'll have a buffer called the number of bytes. So for this particular iteration of the SSL data that we're sending, what exactly is the buffer size? So that is going to be a num underscore bytes, which will be a usize. Cool. And this will also be public. Cool. Now in here, let's create this. So we're going to say data is let data SSL data equals. Cool. We can assign all of that. Now, how do we actually send this data into our user space? So for that, we're going to use something called the PerfEventArray. So eBPF essentially has a lot of inbuilt maps which let you define ways in which you can, which let you essentially define patterns in which you can send data between your kernel space and your user space. The kind that we're going to be trying out today is called the perf event buffer. And a perf event buffer is strictly for one-way communication from your kernel space application to your user space application. It does not allow communication the other way. So your user space can't actually send data to your kernel. We'll be learning about those kinds of maps and structures later on. But for now, let's just do a normal perf event array. So for this, we have to import a macro called a map, and we can define our static perf. Let's just call it events for now. And this is a perf event array. You need to give it a type, which will be our SSL data, and we can call the new method on this. Cool. So it's going to create this perf event array. Now all we have to do is just send data to it. So it's going to be events dot output, and we just need to give it the context and the data and whatnot. Let's get rid of the reference there. Cool. So let's take a look at if this throws any errors right now. We're not reading any of this data in our user space application, and that's fine for now. But let's take a look at if it's building properly. Cool. So it gives me a error, and that's because since I'm giving my BPF probe read an array of the size of number of bytes, like my maximum size over here, that will essentially that will exceed all of my bounds, right? So I need to give it an internal buffer value, like internal amount of the size of the buffer that I need to read. And let's do that real quick. So I'm going to create a new variable called let buff size, and that is going to be the result of a match statement. In my match statement, what I can essentially tell it is that if it's between 0 and 200, so I need to match the number of bytes here. So if it's between 0 and 200, I can essentially tell it to just go ahead and consume the number of bytes. However, if it's greater than 200, so if it's 200 or greater, then I can just limit that to 200. I think that's pretty good. And at this point, I can use this right here, and let's build our application once again. Oh, right, my bad. So let's get rid of the unsafe, the pointer dereference over here, because this is essentially making this become a very huge number. So that doesn't really make sense. This is a pointer to an integer anyway, so we can get rid of the unsafe operation, and we can compile this once again. Great. So now that our Rust application is, our eBPF application is finally running, we can just try to perform a command line operation real quick of a curl. So let's do that. Google.com. Cool. So we're getting some sort of an output. Not really sure what we can do with this yet. So now that we've got our perf events being pushed onto this abstract concept of an array, let's actually extract these events on our on the side of our user space application. A quick look at the documentation for the perf event array will actually let us know how we can actually get data out of this. So a perf event array is unique to every CPU. So if you've got a 4-core CPU, you've got 4 perf event arrays that will be coming out of your application. So you essentially need to poll through all of those 4 arrays and actually extract data. So let's take a look at how we can achieve that real quick. We'll get rid of all of these tabs, close all tabs, and let's open up our main application, which is running on the user side. Cool. So now that we've got this, we are going to perform an attachment onto the perf array, and that can be done simply by calling a let mute perf underscore array equals, and this will be an async perf event array. And now you have to give it the name that you essentially have to let it know how it can access the array from the eBPF application. and that's going to be by calling the try from method. And on your eBPF program, you're going to call the take map method, and we had called our map events, if you remember. So if I open up the eBPF application real quick once again, you can see that it's called events. So that is the exact name that we'll be using over here. And finally, we can, let's see, we can unwrap any errors in here, and we will have to add a question mark here. Cool. So we've got our perf event array. It's an asynchronous abstraction. So we can essentially loop through all of our CPUs now. So let's do a for CPU ID in online CPUs. So online CPUs is a method that is present in, I believe, the Rust, sorry, it's in the IA standard, like sort of, it's a helper function that IA provides. And in here we can do a map error. So all of this is from the IA documentation itself. It's very straightforward. Let's real quick map our operation, and let's do that. Cool. Now that we've got a for loop running for each CPU that exists, we can essentially spawn a task, and this task will essentially be tasked with this task will essentially keep polling the map for each of these CPUs, and it will actually print out any of the data that comes in. So let's create a buffer real quick for that, and that is going to be a buff which will be a perf array dot I believe open. Yeah, it's going to be open, and you open the CPU ID in here and you give it a none. So if you take a look at this, this is essentially us opening the perf event array, and you can give it an initial page count as well. For now, we're going to be giving it none. And once we've got this, we can spawn our tasks. So let's use the Tokyo task construct, and we can spawn an async task. And let me import that as well, actually. So I'm going to import that from Tokyo. Great. So in here, I will call a let mute buffers equals. So we can have multiple buffers for all of these. Essentially, it's the number of events you want to be querying at once. So for now, 10 is a good number. So essentially, in every loop, every iteration of your application of your task, how many, what is the maximum number of elements that you want to extract? And for us, it's going to be 10. Then we can map that into a let's see, it's going to be mapped into a bytes mute construct with capacity of 1024 bytes. So this is the maximum size that our object is going to hold, and we will have to collect all of that into a vector, obviously. Great. So now that we've got this going, let me fix whatever is causing this problem. Let's see, what did I do wrong in here? Let mute 0 to 10, map bytes mute with capacity. I believe I have not imported. Right, let's import bytes mute. So we are going to do a use bytes mute. Oh, sorry, this might be why. Cool, import that. All right, it's going to import the bytes crate, so let's let it do that. Cool. Now that we've got this going, we've got our buffers, we've got all of the like sort of the boilerplate that we needed. We can actually start reading these events. So let's create a loop for that, and in the loop we are going to create a variable called events, and that will be our buff.read events. Let's unwrap this here actually, so we can call it directly. We can do a read events. And in here, you need to give it the buffer that will be getting populated. So that's our mute buffers here. And we can, let's see, we can await that. So cool. So this is going to block the task until there's data to be fetched from our buffer. Now we can go in and for each of these events for buff in buffers dot iter, let's see, iter mute take, we're going to take the events dot read directive here. And if you're curious about what this is, it's essentially sorry, it's events.read. So it's essentially it's eventually getting all of the events that have been read out of the array, and we can loop over. So let's do that real quick. In here, we're going to have to actually extract all of this data and convert that into our SSL data structure. So for that, we're going to create a pointer, let ptr equals, and this will be our buff.as pointer. And then you can cast that into the type of element that this is going to be. So that will be our SSL data. So it's going to be as const SSL data. Now, obviously, we have to actually dereference the structure as well. So let's do that real quick. And I'm not sure about the as a reference here, but we'll take a look at if this causes problems, we'll change our approach. But now that we've got this, we can straight away print this data in our console. And this is going to just be, let's see, let's just print data dot buff. And the number of bytes is going to be data dot num bytes. Okay, that's cool. For now, let's just print the whole thing. I think it'll be fine. Or what if I was to give it a, yeah, that works. Cool. So we've got all of this going. Let's go over all of this once again. What we've essentially done is we've run a for loop that goes over all of our online CPUs, and it essentially spawns a task. This task then creates the buffers, like it creates a buffer with a maximum capacity of the maximum number of events that you want to be gathering. And finally, it essentially loops through all of those. It loops through in every task, and it waits for events. And as soon as an event is reached, or as soon as there is a bunch of data in the buffer, it's going to run our for loop, and it's going to take all of those events, and it's going to print that onto our console. Let's compile this application and run it, and let's see if it runs on our first try. Cool. So it's done compiling. Let's give it a curl. And as you can see, we're actually getting some data out of this. We're actually getting, it's a bunch of gibberish, obviously. We don't really know what's the underlying data behind this, but we're going to get to that real quick. Cool. Now that we've got this, let's convert this into actual text. So I'm going to create a different method here called print data actually. And we're going to pass in data as a reference to this function. Let's create this function, and in here it's going to be called data. Data is fine. Yeah, let's just keep it as a reference instead of a double reference. Cool. So in our data, in this structure of SSL data, we've got the raw buffer as well as the number of bytes that we need to read out of this. So let's real quickly do that. So we're going to say for I in 0 all the way to SSL, data dot num bytes. We're going to create a loop, and it's essentially all we need to do is we need to check if the ASCII character that's being sent to this buffer is printable or not. So it's a very trivial process. All you have to do is call a is let's define it as well in here. So let's call it character. So c equals data I, and we're going to do a if c dot is One second, what's wrong here? Oh, sorry, data dot buffered I. So is ASCII, I believe it's called graphic. Yeah, is ASCII graphic. So that essentially lets us know if the if the character is something that is printable. So it's going to ignore stuff that cannot be printed, whether that's your carriage return or your tabs and whatnot. So we can we can ignore that. Even your null character, null terminator, and all can be ignored straight away. So let's just print that as it is. And we're going to have to, just so that it's a little more readable, we're going to have to do a little more in here. So if it is c dot is ASCII white space, actually, let's just make it an or over here. Or c dot is ASCII white space. Let's print that. Cool. Great. So we've got all of this going. Let's see. Right. Finally, all we need to do is just end this line in here by with an empty println, and that should be, we should be good to go there. Cool. Let's see. Awesome. So I've performed a curl. Now all of this is a little illegible of sorts, but we're going to make it easier to read. The problem here is that this is an HTTP 2.0 request, so it's a little gibberish filled, but we are going to make it a little easier to read by performing an HTTP 1.1 request. Cool. So now we're getting all of this data. So earlier we were, along with the HTTP 2 request as well, we were getting all of this data, but the HTTP 1.1 standard is a little easier to read in plain text. So we've got our GET request, we've got our HTTP 1.1 indicator, we've got the host name, we've got our user agent, and the kind of encoding that our client accepts. Let's try adding a lot of data into this. So if I send like a bunch of data, cool. I've sent a bunch of data, but you can see that the index essentially goes out of bounds because it cannot deal with that amount of data, right? That's essentially because what we're storing in the data num bytes is, let me get back in here, in our eBPF application. Let's see, where's that? Cool. In here, we're storing num bytes here, and here, instead of storing num bytes, we should be essentially storing the buff size. So let's do that real quick. All right, and we'll compile and run this application again. So when we've essentially given it a lot of data, it is printing this for now, but let's give it even more data. So let's go outside our 200 character limit. Okay, so as you can see, we've gone over our 200 character limit, our 200 byte limit. So the data is essentially getting truncated. Now, what if we wanted to actually print all of the data, even though it might be over 200 bytes? So this is where our concept of loop unrolling comes in. We cannot really perform a loop in here we cannot really send all of the data without actually performing a loop unrolling. So let's do that. Essentially what we need to do is we need to calculate an offset. Let's call a let offset equals 0, and we're going to be looping through all of this until the offset is essentially completed, until the offset either exceeds the number of bytes or it ends up essentially printing out all of our buffer. So we're going to run a while loop, and that's going to be while offset is less than number of bytes, and I'm going to move all of this code in here. Now obviously I need to increment the offset every time, and the offset is going to get incremented by my buff size, that is the number of bytes that have been read, and that is going to have to be mutable. Yes. Okay, so we've got this. Let's build our application, and let's try performing the curl once again. Actually, before that, we need to make a few more changes. We're going to have to define a remaining variable here, and that is going to be our num bytes minus our offset. And obviously, if remaining is 0, we can just break out of this. Cool. Okay. And in here, let's see, we will have to, this is fine, chunk size. Let's make this remaining, and finally, we'll have to actually increment this with our offset. So once we've done this, let's compile our application again. And let's run this. Right. So the problem we're seeing here is that the verifier has not really signed off on our BPF application. That's because since this is a while loop, the verifier doesn't really know how long it's going to go on for. For all it knows, that this might just be an infinite loop and it'll keep going. And if you remember from the first video, one of the conditions of a BPF application is that it has to quit. It has to be deterministically proven to be able to quit. So this is not really a Turing complete system, right? So let's help the verifier a little bit. All I'm going to do is I'm going to add a log here, and it can be any log. It's just something to let the verifier essentially get a hold of itself. And if I was to compile it this way, you can see that as soon as the compilation finishes and the BPF prog load syscall is called, it's going to throw an error saying that the last instruction is not an exit or a jump. So how do we fix this? Well, the way to fix this is by adding a strong upper bound. The way you can do that is essentially you have to define a constant. So let's define our constant with const, let's call it max read chunks. Max read chunks. And let's say this is going to be a U size. And you can define an arbitrary size over here. So for example, since these are 200 byte chunks, 200 into 10 I think is 2 kilobytes of data is is a good number to have, and we can say that the max read chunks is 10. And in here you have to create a for loop instead of a while loop, because a while loop is a little difficult for the verifier to be able to deterministically assert. So we are going to change this into a for loop, and that's going to be for I in 0 all the way to max read chunks. And let's compile it once again. So this time over, we get a different error. And that error is essentially because since we've got our logger over here, it's actually creating a lot of data on the stack, and that is causing the stack to overflow. So we can get rid of this line because we don't really need it. And we can compile our application once again. And let's see if it helps this time. All right, so let's perform an SSL request. And as you can see, we're getting all of the data. Along with that, we're getting the entire untruncated data of sorts, as opposed to previously when the data was getting truncated. And that brings us to the end of this video. In this video, what we've essentially done as a recap is we first created a UProbe on an arbitrary function in the SSL library. Then we learned how to send data from our kernel space application to our user space application using PerfEventArrays. And then we overcame the limitations that eBPF applications have, where we cannot exactly use loops. We cannot use unbounded loops. So we created a bounded loop that lets us share all of the data despite having a limitation of the stack being a maximum of 500 bytes. So I hope you enjoyed this video. In the next video, we'll hopefully be going over looking into hash maps, where you can send data from your user space to the kernel space as well, as opposed to only being able to send data from the kernel space to user space. And we'll be looking into XDP, which is the Express Data Path program type of BPF, which lets you essentially perform network operations before the packet even reaches into the kernel's networking stack. So that's pretty cool. I hope you're excited for that, and hope you enjoyed this video, and bye bye.